You see the presentation?
Yes.
Oh, okay. Hello, everyone. My name is Armin. I am working in KTH. I'm going to introduce this 3D micromachined micromechanic low loss, low weight, reconfigurable satellite components. We are going to discuss about the motivation and the research flow, and then I'm going to show you some results of the fabricated devices. First, we are going to see how the work progress is going on. I mean, the review and the studies are done, the simulations are already done. The first fabrication run is finished. We have tested the devices. I would say some devices, not all of them, and then we are going to do the second fabrication run in February 2022, and I hope it goes fine. And then we have submitted the paper to UCAP, and we are working on a journal paper now, and we expect more to come. The motivation behind the work is having a low loss components, which are very compact and low weighted and robust to the harsh conditions of the space. But the most important thing is they must be reconfigurable and have we can reuse them in different frequencies. I'm talking about the antennas, filters, amplifiers, and everything. And the requirement for that is to have a good switching circuit with high isolation and very low loss. And we are interested in high frequencies ranging from 220 to 300 gigahertz for now because of high resolution and also high broad, a lot of bandwidth that is available in that frequencies, which can be used for high data rate communication between the satellites and maybe a satellite to the airborne. And the technology that we choose to work on and implement the designs is silicon micromachining. To be more exact, it's RF MEMS devices, which has very low loss. They are very compact and has a repeatable fabrication procedure. The precision is very high, and with this implementation technique, everything can be implemented on a single chip, and we can have a system on chip device. I'm going to show you some results. The first one is this is a 32 by 32 array antenna. In this antenna, not even the amplitude is tapered, but the phase also is tapered to have a uniform phase all across the antenna array. The 10 dB beam width is reduced by 8.5% in E plane and 10.5% in H plane, comparing to the antennas that do not have this phase compensation. You can see that the S11 we have a fractional bandwidth of around 37%. The side lobe level is below -20 in the whole frequency range that we want. It's from 205 to 295. And then the gain of the antenna is getting up to 37.6 dBi. And you can see the radiation pattern on different frequencies, which is quite, I would say, uniform and constant, because the side lobe levels are not coming up, and it's fine. For measuring the radiation pattern and the antenna specification, we made an anechoic antenna chamber, which has automatic robots to rotate the RX. And we are, you can see here that we mount the TX, and then the RX will be mounted on the robot. It will rotate and we can measure the 3D pattern of the antenna that we want. Then we work on a beamforming radar chip, which the results are not published yet, so I can show very much detail about them. The size of the chips are 11.8 millimeter to 18.2 millimeters, and this is the whole switching network and the front end of the radar. We are using WR3.4 standard waveguide ports for exciting the structure, and this is we excite from side of the stack chips, and then the antenna is on the other side. So it's very compatible with the setup that we have. And the only thing that I can show is this one. You can see that it's quiet as expected, and we have 17% of fractional bandwidth from 220 to 260 gigahertz. We have a beamforming of plus minus 20 degree in azimuth with this antenna with 10 gigahertz of bandwidth. In the switching network of these components, we are using a switch which short circuits the electric field, and then in the blocking state it will short circuit everything, and in the non-blocking it will be open and the wave can go through the waveguide. So the basic is to short circuiting the TE10, which is the dominance mode of the waveguide. Then this is the fabricated switch. This is 2 SPST, which can be used to get 1 SPDT. Then this fabrication run is just for demonstrating and functionality of the model. It's not moving for now, but we are going to implement a movable switch in the next fabrication run. And to measuring it, we just fabricated the interposer, which Mohammed Mehrabi did most of the work, and fabricated this interposer. And then the antenna itself is fabricated on a separate chip, which is 10 millimeter to 15 millimeter to check on the operation of the antenna and to see if it works or not. This is the fabricated antenna, and the dimension and everything are as expected, I would say. This is the S11 of 3 prototypes that we just manufactured. Implemented. As you can see, it's below -10 in the frequency range that we want, and you can see that it's following the simulation. The simulation is just the blue one, and then these are the 3 prototypes. It's following the same trend. And we have 34% fractional bandwidth for this one. The next step is to design more reconfigurable antennas with higher efficiencies and more scanning range, which the beam can easily be changed into azimuth and elevation, and implement the filter banks with low loss and high isolation between each channel. And we are working on higher isolation switches up to 40 dB. RF switches, not just DC ones. Yeah, that was it. Thanks for your time. I would be glad to answer your questions.
Okay, so maybe I can jump to ask question first. And very interesting talk, and to me it's quite challenging project, and for a device working over 200 gigahertz. Okay, and the one slide you show the 2x8 array. Okay, yeah. This no. Yeah. The next one. No. You show the one. This one. Yeah. So I'm not quite understand. Is this based on the liquid wave antenna? And radiation is an in the fire, right? Direction.
The direction. I mean, these antennas are. I mean, every raw has amplitude tapering, but we are feeding this lower raw and the array and the upper part with different phase to change to sweep the beam into azimuth.
So where is radiation direction is?
Yeah, the radiation direction is end fire, right?
End fire, right? Okay. So you can start more to get the high gain, right?
Yeah, we can increase the number of these antennas, and yeah, we will get a higher gain with a bigger aperture. That's for sure.
Thank you.
Okay, we have another question from Elijah, if I pronounce it correctly.
Yeah, that's correct.
Yep.
So I'm Elijah, and I'm currently with OneWeb with the Technology Innovation Group. So we quite interested in like next generation technologies for satellite payload. So with this, my question essentially is just two. You've looked at the very, very high frequencies. How does this translate to Q band, K or V band? Because most of our implementations, other implementations, you've got Starlink, Kuiper, OneWeb. Most of our platforms are K, KA, Q, V band. Even for the next few years, the next 5, 6, 7, 8 years, it's still within those bands. So I'm interested to see how does this translate to those bands, because we're all interested in reconfigurable front ends on the payload. Yeah,
for those frequencies, using silicon micromachining is overkill. I mean, by the silicon micromachining, you get the precision up to microns or even sub-microns. And then in those frequency range, we don't need that high manufacturing precision. And the other thing is the surface roughness that we get with silicon micromachining. In these frequencies, I mean, 250 gigahertz or something, surface roughness is very important in terms of loss, because every dB is, as you know, every fraction of dB is important. So this we are just researching on this fabrication technique for high frequency and future application stuff. For that frequency range, I mean, KA, W band, KU, and these things, I think this milling machines is good enough. And yeah, we haven't looked through that frequencies, but we are just you know, researching to see how this implementation technique influence these frequency components.
Okay, fair enough. So from an application point of view, so are you expecting, or do you reckon satellite filings, ITU filings will move to this frequency band?
Yeah, for sure. It's not possible for satellite to Earth communication because of the path loss and everything. But between satellite communications and you know, in a space for you know, having high resolution for scanning, I think this frequency range can be used.
That's okay. Then the other thing I was going to find out, the gain of this antenna you've presented. What's the value at?
Yeah, this is a 32 by 32 antenna. The gain is 37.6.
Okay.
At the higher level, and here, which is the lower end of the frequency, is 34.7, I think. So I would say, comparing to the other corporate feed antenna, this one is comparable to the other antennas, with better 10 dB beamwidth performance, because the phase is compensated all over the array, and every aperture has a constant phase, I would say, equal phase together.
All right then. Thanks a lot. That's all right.
Yeah.
So if we don't have any